have been considering Myhill-Nerode theorem. Let us go through the statement again. Myhill-Nerode theorem states like this: the following three statements are equivalent. L contained in sigma star is accepted by a FSA. We can take as a DFSA. Second statement is L is the union of sum of the equivalence classes of a right invariant equivalence relation of finite index. And third condition is let equivalence relation RL be defined as follows: X RLY if and only if for any z in sigma star XZ is in L exactly when YZ is in L, then RL is of finite index. Now, we have proved this result by showing that 1 implies 2, 2 implies 3 and 3 implies 1, right. So, actually we started with machine M and defined an equivalence relation Rm on M. Rm was of finite index, it is right invariant, right, and L is the union of sum of the equivalence classes of Rm. Then we saw that if you take RL, Rm will be a refinement of RL. So, the index of RL or the number of equivalence classes in RL will be less than or equal to the number of equivalence classes in Rm. Our index of RL will be less than or equal to the index of Rm. Because this is finite index, this will be finite index. And from this you constructed a DFSA M dash. For the third proof, that is 3 implies 1, from the relation RL you constructed a machine M dash. Corresponding to each equivalence class of M dash, you had a state in M dash, and the equivalence class which contains the empty string is it corresponds to the start state, and if X is in L, then an equivalence class corresponding to that will be a final state here. That is what we read. Now, we illustrated that with one example. Let us take one more example here. Look at this state diagram. It is a DFSA. The alphabet is 0, 1 here. Now, what sort of strings will be accepted by the machine? Q2, Q3, Q4 are final states. So, starting from Q0, you can read any zeros, and if you go to if you read a 1, you go to a final state. Then if you read some more zeros, still you remain in a final state, but if you read 1 extra, you go to a non-final state. Once you go to Q5, you keep on remaining in the Q5 and no string will be accepted. Q5 is a non-final state. So, what sort of strings will be accepted? Any string having just exactly 1, 1. If it does not have any 1 also, it will not be accepted. If it has got 1, 1, it will be accepted. It can be followed by some zeros also, but if it has got 2 1s, it will not be accepted, right. 2 or more 1s, it will not be accepted. So, actually it corresponds to 0 star 1 0 star. It corresponds to this regular expression. The language accepted corresponds to the regular expression 0 star 1 0 star. Now, if you consider this as a M, the machine M, M induces an equivalence relation on sigma star. What is that equivalence relation? The set of strings which take you from Q0 to Q0 is one class, Q0 to Q1 one class, Q0 to Q2 is one class, Q0 to Q3 is one class, and so on. Okay. So, one class J Q0, I will write it as J Q0 or maybe J 0, simpler. J 0 is the equivalence class which contains the strings which take you from Q0 to Q0. What sort of strings will take you from Q0 to Q0? Q0 to Q0. Epsilon will be there, then 0 0 0 0 0 0 will take you to Q0, even number of zeros will take you to Q0, right. So, J 0 contains the strings corresponding to 0 0 star, even number of zeros. J1 is a set of strings which take you from Q0 to Q1. What sort of strings take you from Q0 to Q1? Odd number of zeros, right, 0 or 0 0 0, 0 0 0 0 0 and so on. So, J1 corresponds to 0 0 star 0. I mean I am writing the, instead of writing the language I am writing the regular expression for that. And what is J2? J2 is a set of strings which take you from Q0 to Q2. What sort of strings will take you from Q0 to Q2? 1 takes you, and any even number of zeros followed by a 1 will take you to Q2. Okay? So, that can be represented by the regular expression 0 0 star followed by a 1. And J3 is a set of strings which take you from Q0 to Q3. What sort of strings will take you from Q0 to Q3? Odd number of zeros followed by a 1. So, that will be 0 0 star 0 1. And what is the equivalence class corresponding to Q4? That is set of strings which take you from Q0 to Q4, J4, that is after getting an even number of zeros or an odd number of zeros you get a 1 and then you get one more 0. It can be followed by any number of zeros. Okay. So, J4 corresponds to, you can have odd or even number of zeros, it does not matter. Then 1 1, right, then at least 1 0, you can have any zeros followed by a 1 and then at least 1 0, it can be followed by any zeros, right. J5 is the set of strings which take you, after reading 2 ones you will go here, in between you can read zeros also. So, it will be 0 star 1, then you can read some more 0 stars, I mean some more zeros and another 1. So, if you read number of zeros and get a 1 you will go here, then you can read zeros or you need not read zeros. If you read a 1 1 you will go here, then afterwards you may read 0 or 1, does not matter. Now, look at the set of strings on sigma star, they will belong to any one of these class. Take any binary string, it will belong to one of these classes, right. For example, let me take 0 1 0 0 1, something like this. To which class it will belong? 2 ones means it will belong to J5, right. If the string contains 2 ones or more, it will belong to J5. If it does not contain 1, it will belong to this. If it contains only 1 1, it will belong to one of them, right. If I take for example this, it will belong to this class. Now, what is L? L contains these 3 classes, these 3 are the final states. So, L is the union of the equivalence classes corresponding to these 3. Okay. So, L is J2 union J3 union J4. Right. Now, according to Rm, that is, this is the machine M, and we have defined Rm as the set of strings which take you from initial state to a particular state, each one corresponds to a equivalence class. So, it has got 6 equivalence classes like this, and Rm language is the union of 3 of them. Now, consider RL. RL will be a refinement of, Rm will be a refinement of RL. So, some of these equivalence classes can be merged in RL, right. In RL, some of the equivalence classes can be merged. See which of them can be merged. You see, if you take a string from J0 or J1, it will be of the form a sequence of zeros. If you take a string which belongs to the equivalence class for this or J0, and if you take a string from J1, they are a sequence of 0, whether it is odd or even is the difference, right. If it is followed by a string which has 1 1, you will accept it. See, I take 2 strings x y, one belongs to J0, another belongs to J1. That means x is even number of zeros, y is odd number of zeros. If I take a z like this, then if z contains only zeros, it will not be accepted, whether it is xz or yz, both will not be accepted. If z contains just 1 1, both of them will be accepted. If z contains 2 1s or more ones, both of them will not be accepted. So, whatever may be z, xz and yz will both be accepted or both be rejected, right. Is that clear? So, you can in RL, if you consider RL, J0 and J1 you can put in the same equivalence class. And what about J2, J3, J4? Suppose I take one string from okay, I will consider J0 and J2 now, J0 and J2. X belongs to J0, y belongs to J2, right. That means x is a string of zeros alone, y contains 1 1, right. Now, if I take a z and I take z to be 1, xz will be accepted because it has 1 1, yz will not be accepted because it has got 2 1s. So, xz can be accepted, yz need not be accepted, will not be accepted, and I choose z in such a way that one is accepted, the other is not accepted. Okay, so, that does not satisfy the condition of RL, is not it. So, J0 and J2 cannot be in the same equivalence class of RL, you cannot merge them. Similar argument holds for J0 and J3, J0 and J4, J1 and J2 and so on. You cannot combine any of this with this, right. But look at J2 and J3, J2 and J3, take a string x and y. X has 1 1, y has 1 1, So, if you take Z, if Z has zeros alone, both xz and yz will be accepted. If Z contains 1 1, both 1 1 or more ones, xz and yz both will not be accepted. So, whatever way you choose Z, either xz and yz will both be accepted or xz and yz will not be accepted, right. So, they will be in the same equivalence class. A similar similar argument you can give for J4 also. So, actually in RL, J2, J3, J4 will be merged, and J5 is of course that if you take one string from J4 and J5, say for example J4 if you take and J5 if you take x and y, this has got 1 1, this has got 2 ones or more ones, right. If I take Z such that Z is equal to 0, xz still has 1 0, yz has more zeros. So, xz will be accepted, yz will not be accepted. So, you cannot sort of put J4 and J5 in the same equivalence class of RL, they will be different. So, J5 forms a separate class altogether. So, according to RL there are only 3 equivalence classes: strings which do not have ones, strings which have 1 ones, string which have 2 or more ones. Okay. So, if you put them as a J0 union J1, J2 union J3, union J4, J5, and epsilon will belong to J0, right. So, epsilon will belong to this, that will be the initial state, and J2, J3, J4 contain the final states or strings in them are accepted. So, that will be the final state. The transition diagram will be like this: as long as you read a 0, you are here. If you read a 1, you go here. If you read one more 1, you go here. How did I get this transition diagram? By the way you have defined, see this has epsilon in that. Actually epsilon is the equivalence class containing epsilon is this. The equivalence class containing 1 is this. The equivalence class containing 2 ones is this. So, what is the equivalence class epsilon concatenated with I am sorry 0? That is again here, no, it is the same equivalence class. So, this R goes here. What is epsilon concatenated with 1? 1, that equivalence class is this. So, this R goes here, and with 1 if you concatenate 0, 1 0, to which equivalence class 1 0 belongs? It will be here. So, 0 goes here. If you concatenate with 1 and 1, 1 1 belongs to this class. So, arc 1 goes here. 1 1 0 belongs to this, 1 1 1 also belongs to this class. So, that arc goes like that. This is the way you have constructed the minimum state. This is the minimum state automaton. This is also a deterministic automaton. This is also a deterministic automaton, but this is the minimum state automaton. Okay. So, you have the result the minimum state automaton accepting a language a regular set is unique up to an isomorphism. And actually it is given in the theorem and given by m dash in the proof of Myhill-Nerod theorem. So, in the Myhill-Nerod theorem we started with m and then constructed m dash, right, for RL, and that gives you the minimum state automaton. What is an isomorphism? Renaming of states. Instead of calling them as like this, I can call it as some q naught q1 or p naught p1 p2, something like that. That is what it means. Now, how are you justified in saying that? Okay. How are you justified in saying this? First of all, in the theorem if you look, you started with L accepted by M, constructed the relation Rm, and we constructed RL and then M dash. This is the way the proof went. Now, we saw that Rm is a refinement of RL. So, the number of equivalence classes in RL is less than or equal to the number of equivalence classes in RL. So, any DFA if you start with, you can reduce and have a machine corresponding to RL, right. And if two have the same number of states, you can say one has the same number of states. Suppose I start with this, I start with m, another one say m bar say, then I reduce according to RL and get m dash, here m bar dash. Both are RL for L. So, actually they will be they will have the same number of states, which is equal to the number of equivalence classes of RL. Now, you can identify each one of them. I have two automaton m dash and m bar dash. This has got q naught q1 qn minus 1 say, this has got p naught p1 pn minus 1. Now, the initial states correspond to each other, and if a string x takes you from q naught to q1, another string x will take you from p naught to some pj, right, and qi corresponds to pj. Like that each state can be identified with another state. So, that will be, this identification is consistent. You are making a correspondence between the states of m dash and m bar dash, and this is consistent because they are all defined due to the equivalence classes of RL. Okay. So, the minimum state automaton is unique up to an isomorphism. Now, we learn a few more definitions. I will use that example again. Now, you see that you are given a DFSAM, and in that you are having two states PQ. Two states you are having in the diagram, state diagram of M. You say P is equivalent to Q. You say, you define like this, you say P is equivalent to Q, or you write as P if for any x in sigma, sigma is the underlying alphabet, delta of Px and delta of Qx are both in L or both not in L. This is how we defined RL, similar to defining RL. Toot says P and Q are equivalent if you take any string starting from P, after reading X you go to a state, starting from Q after reading a particular string you go to a state, another state. Both of them should be final states or both of them should be non-final states, or are both in L or both in F or both not in F, final state. Delta Px is a state, right. So, that is what this meant. Okay. Starting from P after reading a string X you go here, starting from Q after reading X you go to another state. Both of them should be final states or both of them should be non-final states for any X. Then you say P and Q are equivalent. P and Q are distinguishable if there exists a X, if there is a X such that delta of Px and delta of Qx, if you consider, this may belong to F and this does not belong to F. One of them may belong to F, other may not belong to F, or vice versa. This may belong to F, this may not belong to F. If there is a string X which takes you from P to a final state, but takes you from Q to a non-final state or the other way around, then the states are distinguishable, and X is called the distinguishing X is called the distinguishing sequence. X is called the distinguishing sequence. Now look at this example. You take Q0 and Q1. If you get a 1 or if you get a string which has 1 1, it will take you to a final state from both, otherwise it will take you to a non-final state. So, any string X you take, either it will take you from Q0, any string X if you take, either it will take you to a final state starting from Q0 or Q1, or it will take you to a non. So, they are equivalent, right. Similarly, if you consider Q0 and Q2, they will not be. From Q0, if you get a 1, you go to a final state. From Q2, if you get a 1, you go to a non-final state. So, 1 is the distinguishing sequence here. Q0 and Q2 are distinguishable, and 1 is the distinguishing sequence. So, now coming back here, P is equivalent to Q whenever you, if you take any string X, it should take you to a final state and this should take you to a final state. Now, I have one symbol. Suppose some A, it takes me to a state R, the same A from Q, it takes you to S. Now, if P and Q are equivalent, what can I say about R and S? They have to be equivalent. Any string takes you to a final state or takes you to a non-final state in both cases. So, if it begins with the A, it will go to R and then it will be followed by the x you are writing as some ay, that is all. So, if ay is x from P, if ay is accepted, from Q ay will be accepted, that is from R y will be accepted, from S y will be accepted. So, R and S will be equivalent. So, if P is equivalent to Q would imply R is equivalent to S. The other way around, if R is not equivalent to S or contrapositive, if R is not equivalent to S, there is a distinguishing sequence which takes you in one case to a final state, in another case to a non-final state. That means that string y which takes you in one case to a final state, in another case to a non-final state. Consider ay, in one case it will take you to a final state and one case it will take you to a non-final state. So, if R and S are distinguishable, P and Q will be distinguishable. So, the other way around, R are distinguishable, I am writing it not equivalent, that would imply P and Q are distinguishable. So, this is the concept. So, we have seen in this case what is the class, equivalence class, how you can group the equivalence class and so on. So, okay, so for every example we cannot do that to get the minimum state automaton. The shortcut is like this, or you have all of them Q0, Q1, Q2, Q3, Q4, Q5 in one block. Then separate them into two blocks having final and non-final states. So, Q0, Q1, Q5, the possibility is these can be equivalent. Then you keep on separating them so that only equivalent state come in a one block. You partition, you are going to partition them. Q2, Q3, Q4, this is one block. Why? Epsilon takes you from this to a final state, epsilon takes you from this to a non-final state. So, if you take one from this, they are distinguishable. Epsilon is the distinguishing sequence. These are the final states, these are the non-final states. And epsilon takes you from each one of them to a final state, epsilon takes you from each one of them to a non-final state, right. So, they are distinguishable. So, this is the first separation. Now, look at this Q2, Q3, Q4, Q2, Q3, Q4. After getting a 0 from Q2 or Q3 or Q4, where do you go? Q4. Okay. The next state is the same. In this example, it so happens it is the same. So, after going to Q4, either it will be accepted or not accepted and so on, is not it? And this is a final state. And after reading a 1, where do you go? From all 3 states you go to the same state. So, further division of this is not possible. It is not possible to further divide this block. Look at this block Q0, Q1, Q5. From Q0 or Q1, if you get a 0, where do you go to? The same block Q0 or Q1. From Q5, if you get a 0, you go to Q5, same block. So, from Q0 or Q1 or Q5, what are the 0 successors? 0 successors means the states to which you go after reading a 0. So, that is Q0, Q1, Q5 only. They are in the same block. So, nothing happens. Now, look at 1. Look at the 1 successors. What are the 1 successors of Q0, Q1, Q5? Q0 and Q1, the 1 successor are Q2 and Q3. For Q5 it is this. So, they are in different blocks, Q5, Q2, Q3, they are in different blocks. So, you have split them, you split them. Q2, Q3 and Q5 are distinguishable. So, Q0, Q1 should be distinguishable from Q5. Is that clear? Q2, Q3, Q4. Now, we have seen that this cannot be further divided, this is a single state. Now, Q0 and Q1, look at Q0 and Q1, what are the 0 successors? Q0 and Q1 the same block. What are the 1 successors? Q2 and Q3, they are in the same block. So, further division is not possible, right. So, you get only 3 states, these 2 states can be grouped together, they are equivalent, Q0 and Q1 are equivalent, you can group them together. Q2, Q3, Q4 are equivalent, you can group them together. This is the idea. One more example we will take. Q0, Q1, Q2, Q3, this is the final state and this is the initial state, Q4, Q5, Q6, Q7, right. The transitions are marked as follows: 0, 1, 1, 0, 0, 1. Zero, 1. Zero, this is a state diagram of a machine. We want to find out the minimum state automaton. Let us find the minimum state automaton in this procedure. So, all of them will be in one block first, there is only one final state and others are non-final. So, first you split into non-final and final states. So, Q0, Q1, Q3, Q4, Q5, Q6, Q7 are in one block, Q2 alone is in one block. Now, look at the 0 successors of them. The 0 successors of Q3 and Q5, Q3 and Q5 are in this block. The 0 successors of Q3 and Q5 are in this block, but the 0 successors of Q0, Q1, Q4, Q6, Q7 are in this block. Okay, right? So, you split them, the 0 successors of Q3 and Q5 are in this block. So, you put Q3 and Q5 separately and Q0, Q1, Q4, Q6, Q7 in one block. Keep on doing this whether further split is possible. Q3 and Q5. What are the 0 successors of Q3 and Q5? Q2. What are the 1 successors? Q6. Same state. So, further split here is not possible. Look at this Q0, Q1, Q4, Q6, Q7. What are the 0 successors of them? Q0, Q0, Q1, Q1 is Q6 in the same block, Q4 is Q7 in the same block, Q6 same block, Q7 the same block. But consider the 1 successors. What are the 1 successors of Q0, Q1 etc.? The 1 successor of Q1 and Q7 are in one block, right. The 1 successor of Q0 and what is Q4? Q4 are here in this block. The 1 successor of Q6 is here. See, the 1 successor of Q0 and Q4, they are in one block. So, Q0 and Q4 you can split. The 1 successor of Q1 and Q7 are in this block. Q0, Q4, the 1 successor of Q6 is in one block. Q6, Q3, Q5. So, this is split into this like this, right. Now, you have to see this, for this no further split is possible, these are single states. So, Q0 and Q4, Q1 and Q7, whether further split is possible you have to see. Q0 and Q4, what are the 0 successors? Q1 and Q7, they are in the same block. What are the 1 successors? Same state, Q5. So, at this stage you cannot separate them out. Q1 and Q7, see whether they can be separated. Q1 and Q7, what are the 0 successors? The 0 successors are 6, Q6 and 1 successors are Q2, same state. So, you cannot split further. So, further split is not possible in this case. So, the minimum state automaton will have 5 states, where Q3 and Q5 will be merged, Q0 and Q4 will be merged, Q1 and Q7 will be merged and so on. So, if you draw the diagram for minimum state automaton, Q0, Q4 will be one state, Q3, Q5 will be one state, Q1, Q7 will be one state, Q6 will be one state, Q2 will be one state. Which will be the initial state? the one to which Q naught belongs. So, this is the initial state, Q2 is the only final state. Now, draw the transitions. Q naught 0 is Q1, Q4 0 is Q7. So, if you get a 0 you go to this. From here if you get a 1, Q naught 1 is Q5, Q4 1 is Q5. So, this is you get a 1. You go here. From this Q3 Q5, Q3 Q5 if you get a 0 you go to Q2. If you get a 1 you go to Q6. From Q1 Q7 if you get a 1 you go to Q2. If you get a 0 you go to Q6. So, from Q6 if you get a 0 you go to Q6, if you get a 1 you go to Q4. From Q2 if you get a 1 you go to Q1, if you get a 0 you go to Q naught. So, this is the minimum state automaton corresponding to this. So, given any machine you can find the minimum state automaton in a systematic manner. The idea of this distinguishing sequences is very useful when you apply the idea of finite state automata to computer networks. You expect the system to be in a particular state. The whole network it is in a particular state. After certain things happen, some messages sent from one to another or some from this to another and so on, there will be the whole system will be in another state. Then after some certain things happen it will be in another state. So, the status of a network can be represented as a state of a finite state automaton. And you start with some initial configuration, then after something you expect it to be in a particular state, you expect the whole system to be in a particular status, but you do not know whether that will happen or not. So, by experimenting you find that it may go to a different thing. So, you want to check. So, for that you have to give proper inputs and check whether what is happening to the system, whole network. Send messages from one to another or send packets from this to other and so on. But what is that you are going to do? What sort of thing you are going to do? How many times you have to test? That really corresponds to you have to find out the distinguishing sequences. If you represent it as a network from one state to another, which is the distinguishing sequence, and you have to experiment only for those distinguishing sequences. You need not have to go through everything, only for those distinguishing sequences you have to find out whether the system behaves as you want it to behave or it is behaving in a different way. So, some sort of that idea, what I am telling you may not be the exact thing, but a similar idea is used for finding out whether the computer network, the system behaves in a way you want it to behave or it behaves in a different way and puts you into trouble. Okay. So, lot of finite state automata idea are used in that context. Now, having done the minimization of deterministic automata, we have considered deterministic finite state automata and minimized it. In fact, if you remember what we did in the earlier classes, we considered a non-deterministic FSA having 2 zeros in the middle or having 2 ones in the middle, and then constructed the DFSA. That was not difficult, but the strings we ended up with 9 states or something like that, right, by subset construction, but the 9 states can be minimized and you get only 4 states, and those which ended with 2 zeros or ended with 1 2 ones, again we constructed and we got the minimum. At the time the construction itself gave you the minimum state automaton, but the subsist construction as it is may not give you the minimum state automaton, but you can minimize that. Okay. So, what we did is from the non-deterministic FSA you constructed the deterministic FSA which had many states, and then you can minimize that using this procedure, you will get the minimum state automaton, right. Now, given a non-deterministic FSA, can you apply this procedure? Can you apply the equivalent states and merge something? Let us see, it is not possible really. So, let us see this example, Q naught see what is the language accepted by this machine. It is a non-deterministic machine, because from Q naught if you get a 0 or a 1 you can go here, from Q naught if you get a 0 you have can go here or here, from Q naught if you get a 1 you can go here or here. So, it is a non-deterministic FSA. What sort of language will be accepted? This is the final state. So, any string ending with a 0 will be accepted, any binary string ending with a 0 will be accepted. Now, if you try to minimize this automaton, Q naught and Q1 is a final state, this is not a final state, they cannot be equivalent, and among this Q naught takes you to a final state, 0 takes you from Q naught to a final state, from here to a non-final state. So, these two cannot be equivalent. If you try to apply the minimization procedure, find out which states are equivalent, this being a final state cannot be equivalent to any of them, and these two, 0 takes you from here to a non-final state, from here to a final state, because 0 takes you from here to Q naught and Q1, two possibilities are there, but anyway they are not equivalent, right, they are not equivalent. So, you cannot minimize this, but is this the minimum state non-deterministic FSA? No, this is not at all necessary. Okay. The minimum state NFSA is just this. So, this minimization procedure does not work for non-deterministic FSA, it will not work, right. So, this is about minimization of DFSA. Next, we have to consider finite state automata with output, which we have earlier considered in the first class, like serial adder, parity checker and so on. So, in that case also you can have a sort of a minimization procedure, but what we would like to consider is how do you define the output. Does the output depend on the state alone, or does the output depend on the state and the input? We have to check. So, depending upon that we call it as a Moore machine or a Mealy machine. This we shall consider in the next lecture. Yes. State Q3 is not reachable from Q naught, that is correct. So, before you start the minimization procedure, you can remove the inaccessible states, but in this case Q3 merges with Q5, but Q5 is reachable. So, it does not create any problem. Starting from Q naught, Q3 will not be reached, but Q5 will be reached.